Now, what is effective atomic number? Earlier, many theories were put forward to explain the stability of coordination compound. One such theory was effective atomic number given by Sidgwick. As per this theory, the central metal will continue to gain a pair of electrons, that is two electrons, from the ligands till it it has electrons equal to the nearest noble gas. So EAN was very easily calculated. The formula for EAN goes something like this. EAN was equal to Z, that is the atomic number of the central metal ion. Now, that central metal ion might have lost some electron, that is its oxidation state, in order to form that complex. So, Z minus X, Z is the atomic number and X is the oxidation state. Plus, there are some electrons given to the central metal by the ligands. So, the entire formula turns out to be Z minus X plus Y, where Z is the atomic number of the metal, X is the oxidation state, and Y is the total electrons given by the ligand. Like for example, if there are 6 ligands attached to the central metal atom, that means they have donated 12 electrons, as each ligand will give 2 electrons. If there are 4 ligands attached to the central metal atom, means it has donated 8 electrons. So this EAN is calculated pretty easily. Like for example, if you have a complex FeCN6 and there is 4 minus charge, that suggests the oxidation state of the central metal is plus 2. The atomic number of the central metal Z is 26. So the EAN becomes Z, that is 26, minus X, that is the oxidation state, that is 2, plus 12, that is 6 ligands has given 2 electrons each. So the EAN comes out to be 36, which is equal to the atomic number of krypton. So Sidgwick suggested that the central ion has only 6 ligands surrounding it. It will not have 5 ligands surrounding it. It doesn't have 4 ligands surrounding it. It has 6 ligands surrounding it, because if there are 6 ligands surrounding ion, the complex will have atomic number 36, which is same as that of krypton, and it should be stable. So this was EAN. However, EAN didn't prove to be correct for all complexes. For many complexes, the theory failed. However, for you, EAN has quite good weightage in your entrance exams. So we will solve a few more questions here and there. If the EAN comes out to be equal to the nearest noble gas, so we will say that it is following the effective atomic number theory, or else it is disobeying. So let's see some examples. For example, the first example is what you have seen in the previous slide, that is K4FeCN6. So here the atomic number, that is Z, is 26. The oxidation state of the central metal, that is iron, is 2, and the electron donated by the ligand is 12. So EAN becomes 26 minus 2 plus 12, that is 36, which is equal to the atomic number of krypton. So this complex is obeying EAN. The second example over here is where you have trisethylene diamine cobalt. So there you have cobalt, which is in which has an oxidation state plus 3. It has 3 ethylene diamine attached to it. So the atomic number of cobalt is 27. The oxidation state is 3, and there are only 3 ethylene diamine. However, ethylene diamine is a bidentate ligand. So one ethylene diamine is going to have 2 points of attachment. That means one ethylene diamine is going to donate 4 electrons. There are 2 nitrogens. Each nitrogen will donate 2 electrons. So one ethylene diamine will donate 4 electrons. And as there are 3 ethylene diamine, so it will make up 12. Here we have not multiplied it by 2, we have multiplied it by 4 because it is a bidentate ligand. So it comes out to be 27 minus 3 plus 12 again comes out to be 36. So again this example is also obeying EAN theory. The next is an heteroleptic complex where you have two different types of ligand, where you have platinum, 2 chlorine and 2 ammonia, and there is no charge on the complex. That suggests platinum is plus 2. The atomic number of platinum is 78, and as there are total 4 ligands, 4 monodentate ligands, so each one is going to donate 2 electrons. So the electrons donated by ligands is 8. So 78 minus 2 plus 8 comes out to be 86, which is equal to radon, again the nearest noble gas. So again this is obeying the EAN theory. Let us go to the next example, that is chromium, a monodentate ligand chlorine, a monodentate ligand water, and 2 bidentate ligand, that is ethylene diamine. So here the oxidation state of chromium is 3, the atomic number of chromium is 24, and the total electron donated by the ligands is 12. As there are 2 monodentate ligands, chlorine and water, so 4 electrons will be donated by them, and there are 2 bidentate ligands, 2 ethylene diamine, so each one is going to donate 4 electrons, making it 8. So the total, there is 12 electrons donated by the ligands. So 24 minus 3 plus 12 makes it 33. So this is disobeying the EAN theory. As I have said earlier, this theory failed for most of the complexes, but still you should know to calculate it. Another example is K3FeCN6. It is slightly different from the first example. The difference is the oxidation state. Again, iron is a central metal. Atomic number is 26. But here the oxidation state is plus 3. Again, there are 12 electrons donated by ligands. However, the EN now is 35. So again, this is disobeying the effective atomic number theory proposed by Sidgwick. Now after EAN, we will try to understand the geometry in coordination compound. Now many theory is put forward to explain the geometry and bonding in coordination compound, namely VBT, that is valence bond.